Hello and welcome to RF Design Tutorials. This is tutorial 13 on getting started with LoadPull simulations. Here's the agenda for this video. We will start with understanding the concept of LoadPull and then go over various LoadPull kind of analysis which we can do in ADS and also understand the data which is generated after LoadPull simulation. The idea behind this video is you gain more design level insight by watching the tutorial than available anywhere else. And I hope after this video, you will be very comfortable running load pull analysis in ADS software. Before we start, subscribe to my channel. Once you subscribe, click on the bell icon to make sure all the notifications are enabled. And don't forget to give it a thumbs up and share it with your friends and colleagues who may be interested in watching similar tutorial. All right, let's understand what is load pull. Load pull is a generic term applied to the process of systematically varying the impedance which is presented to a device under test, and most often than not, it's a transistor. And by doing so, we assess the performance and the associated condition to deliver that performance in a network. Now, while load pull itself implies that impedance variation is happening at the load pole, but the reality is the impedance can be varied at any of the ports of your DOT, such as the source side, and that process we call as source pull. Now, depending upon what figure of merits are we trying to look at, we either perform load pull or source pull. In a typical load pull analysis, we select a region in the Smith chart, which basically represents a set of reflection coefficients or impedances, and we vary them one by one at either the input or the output of the device, and then capture the output and plot contours. Like in this picture, we are plotting contours of constant power delivered at the output and the power added efficiency. By looking at this table, we know what impedances are more suitable for the transistor to give you a specified amount of power or efficiency. It is as simple as that. Now let's go to ADS and understand how we can set up some of these kind of simulation, and then how to understand the data which gets produced after we perform the simulation. So here, to explain the concept, let me start with a very simple bench. Now in this bench, I do have a Cree nonlinear model. This nonlinear model or the design kit can be obtained from Cree website if you have an account. If not, you can go to the Cree's website and apply for an account so that you can download this design kit, which you can see I'm using in my current workspace. Now, out of those transistor models available, I'm using CGH40010, which is the device which works till around 8 gigahertz and can deliver around 10 watt or more power in the frequency range. Now rest of the stuff is very simple, like any traditional harmonic balance simulation, and I have covered harmonic balance simulation, power sweep, multi-dimensional sweeps, and data processing in my earlier videos. If you haven't watched those videos, I will recommend you to watch those first before continuing with load pull, because you will need a lot of those knowledge in trying to do data processing and data manipulation, which you obtain after running load pull simulation. Now, in a traditional harmonic balance simulation, we connect this 50 ohm source and we run simulation and plot the output spectrum. We do the power added efficiency calculation and so on. The difference here, because we want to run a load pull simulation, you can notice I have connected an S1P equation block where I have defined S11 by a variable called GL, and the characteristic impedance or reference impedance is defined as 50 ohm. The GL variable is defined in this equation here, where it is dependent on two variables, rho real and rho imaginary, which I have initialized with some values under the variable block. And using the parameter sweep here, I am performing a sweep of the rho real and rho imaginary variable over certain range. And as you can see the start and stop set here. And these two are nested sweep. This is the outermost sweep where we are sweeping imaginary part of rho. And this sweep is calling sweep 4, which is basically nothing but the name of the sweep, which is sweeping the real part of the row. Now, this creates a nested sweep condition, and the inner variable is calling HP1, which is nothing but our harmonic balance simulator, which you can see currently is set at 2.4 gigahertz. So that's how the simple bench looks like. Now I have biased the transistor in class AB configuration by looking at DCIV characteristics. Now this resistor here is simply helping us to achieve the stability because most of these power devices will be inherently unstable, especially if they are unmatched devices. And I have performed stability analysis to make sure I have the right resistor so that when we look at the performance, it's coming out of a stable device. Now with this setup, we can go ahead and run the simulation. ADS will perform the parameter sweep. At the end of sweep, simulation, you can observe I do have, few things plotted on the Smith chart. The black dots are basically representing the samples or the load coefficients which we have used in the simulation. And then we are plotting power contours and PAE contour. Now, we can calculate the contours by using the simple function here in data display, which is named as contour underscore EX. And then you pass certain parameters based on what you want to calculate. If you want to understand the syntax of this function, you can double click on the equation, go to the documentation of ADS and look at list alphabetically. And if we go to a section which is starting from C, we can look at the function here, contour EX. And here is the complete syntax. Now you have certain arguments to pass, and here are some of the defaults, which has to be passed. Or if you don't specify, ADS is going to use this default. So in here, what I have used is simple data, which is the first argument in this equation. Then I have used the step size and what step I would like to plot the contour. And finally, number of lines. That means how many contour lines would I like to see. So starting from the highest power with a certain increment, how many lines or contour lines would I like to plot. And finally, the interpolation type, because it has three interpolations, 0, 1, and 2, which means no interpolation, cubic spline or B spline. So I have in my data set, I have used option of 2, and that's what you can see here. That's what we are calculating. This P out dBm is a measurement equation where I have calculated the power first in watts, and then I simply converted it to dBm. So it's all very simple harmonic balance simulation, which allows you to look at the typical, very simple load pull simulation. Now, by changing the row range in your schematic, you can play around with the region where you would like to see the power coming out of device. For example, instead of minus zero point 0.8, if I just change it to minus zero point 0.4 to minus zero point 0.2, you can see I'm sweeping in a narrow range and all the contours plot is accordingly coming up. So there is no major surprise here. So let's come back, undo, and rerun the simulation. So this is your first load pull simulation. And here the blue curves are for power contour. The red curves are for PAE contour. And once you start is for the power contour, and you can see the innermost contour is belonging to the highest available power as in the current given condition or the setup I have done. And beyond that, every power contour will decrement by zero point 0.5. You can see here, so 40 dBm, now it's 39.5, 39, 38.5, and so on. And again, by changing these variables here, you can decide how many contours are shown to you. For example, if I just want to see, 5 contour lines in an increment of 0.5 or decrement of 0.5, I can simply change those numbers, and now you can see you are seeing a lesser number of contour lines. Right, so instead of hard coding this number, you can also declare, a couple of more equations here, and you can use those variable names here to control it in a more dynamic fashion. All right, so this is good enough. And then, you have the time domain waveform of the drain voltage and the drain current here to see it's really operating in class AB configuration, because here you can see the current is not conducting the whole sine wave kind of cycle or 360-degree. It's get clipped for certain duration. So it's more than 180-degree of conduction, but less than 360-degree. So this indication it's a class AB operation. Right. So if you are doing your own simple harmonic balance based load pull simulation, this is what you got to do. But in the real power amplifier design process, you need to do much more advanced load pull. And this where you can leverage the load pull design guide, which is available in ADS. So let me show you how can you work your way through the load pull design guide. So here I have a blank workspace, and in this workspace I have already included the Cree design kit to obtain the nonlinear models. And here if I open a new schematic, and let me keep this side by side so that you can clearly see what happens when I start to insert a load pull design guide template. Now under design guide menu, I do have a load pull, and you can see here I have a cascaded menu which makes my job easier. But if you are activating design guide for the first time or using design guide, you may not see this cascaded menu, and that's your preference. You can go to preferences and set it to use cascaded menu. Once you do that, you restart ADS and you will have this kind of menu available. Now, if you look under load pull, there are plenty of templates available for you to use depending upon what you're trying to simulate. Now, the simplest one, if you have a nonlinear model of the device from the vendor you are trying to obtain it from. So the simplest load pull simulation is constant available base source power based load pull. What this simply means at a specific source power, we are going to vary the reflection coefficient of the load and then observe the available power at the output and the efficiency and rest of the parameter. So once we click on that, a couple of things will happen in ADS. The first thing will be that you will have a schematic where you will have a sample template set up for you with a default device, and you can remove this device and put your Cree transistor or any other vendor's transistor which you may be using. Along with this, you will also see this data display with some default plots and some data available for you to use. So we'll go and look at this plot in little more detail in few minutes. And also you can see the new design HP one tone load pull, which is basically this is schematic. And then you have a couple of other subcells, which is basically this instrument because that's a subnetwork. So if we try to push inside this design, you can notice the DC bias setup. And this is very similar to what we did, just now with the basic harmonic balance setup. So these are the connection points where you feed the gate voltage, the drain voltage, input RF power, and this is the drain output connection. And then at the output, remember we connected S1P block. That's actually inside this block here. So if we push in further, so these are these two designs. And you can see similar S1P block here with couple of parameter sweep. Now the equations here are looking slightly more complex because the way we set up the conditions what we want to do make all those changes. So there are plenty of if then else kind of equations written inside. So let's see how can we set up this load pull instrument. Now if we double click on this load pull instrument, we get this property dialog, and that's where we specify the region on the Smith chart and whether we would like to use the Z inputs, which is nothing but impedance inputs directly, or we would like to use the reflection coefficient. So any term which you see here starting with S means reflection coefficient. Anything which is starting with Z is actually the impedance. coefficient format. Some of you might prefer working with Z, and accordingly we need to do this setup. You can set your V bias 1, which is basically gate voltage, V bias 2, which is drain voltage, set your frequency, select the input source power, which you like to feed at the gate of this transistor, select the characteristic impedance. Now, after that, parameters here will get used. So the first decision we make, whether you want to specify the load center in terms of S or Z. Now, depending upon what you specify here, either Z related blocks will be valid for your simulation, or parameters starting with the S will be valid. And at the bottom, you can see the clear description is given here. All right, so once you make that decision, then you go and decide whether you want to sweep a rectangular region or a circular region. So by default, rectangular region is set to yes. And if that happens, you are going to pick the corners using S imaginary minimum to maximum. And then you divide that range into some specific number of points. Similarly, you select S real minimum, real maximum, and divide that range into specific number of points. So this is the concept which I used earlier when I showed you a basic harmonic balance based load pull analysis. Now, if you set it to no, then what happens depending upon whether you have used Z fundamental or in the selection above, or the S load center fundamental, around that point, it will use this radius and it will make a circular region around it. And that circle will be divided in these many number of points. So you will have X and Y grid. So if we select 144 points, that means 12 points on x-axis and 12 points on y-axis. So 12 cross 12, resulting in 144 points in the overall circle. So that's how simple it is. So once you click on any of these parameter, the detail is given here. Now let me show you. I already have one setup done with a Cree device, which will give you a very clear idea how we are going to set up a loadful for a practical device. So if I open the step 3, you can see I've cleaned up few of things. I have replaced the default MOSFET kind of model with my Cree device with a 5 ohm resistor. And if we look at the setting here for the load pull instrument, I can decide the bias, the gate bias voltage. So let's say if I want to change it to minus 2.7 volt, and the drain bias, which is 28 volt, and that's very typical of any gallium nitride device. So this information can be obtained either by looking at datasheet, or you run your DC IV simulation like I covered in one of the earlier tutorial videos. You select your right bias point. The frequency I'm using here is 2.4 gigahertz, and the input source power is 29 dBm for the start with. And to specify the load center, I set S to no. That means I'm going to use the Z load center fundamental. Also, the circular rectangular region is set to no. That means I'm going to use a load radius and then divide the whole region into 144 points. So here is the load, center, which I've selected 20 ohm. And around that point, I'm going to create a circle and divide that whole thing by a certain amount. Now, while performing load pull simulation, you also need to be mindful about your second harmonic on the load and the third harmonic on the load. And by default, they are set to open circuit, which is high impedance. And most of the time that works. But sometime you might need to short circuit them. And then you can define it as 0 plus J0, which will make your second and third harmonic to be short circuited, because all these things will have eventual bearing on what you obtain from at the fundamental output. All right, so with this basic setup, we are ready to perform simulation. And once we run the load pull analysis, we go ahead and look at this data. Now, at first, if you're new to load pull simulation, this data display can look overwhelming or pretty complex. And I've seen some designers actually get scared with this amount of data. But once I go through all the plots, you will be very comfortable and you will find each and every data on this data display page is actually giving you some level of insight into your power amplifier's device operation. So let's start from the top left here. So the first window or the first quadrant, if you want to call that way, is showing you the power contours and the PAE contours, pretty much like how we discussed. And this table gives you a quick insight into what kind of levels you have there. And here you can see under my given circumstances, the maximum power available out of device is around 41.5 dBm, and rest of those are contours in zero point 0.2 dB uh, increment. Similarly, the efficiency, the maximum efficiency obtainable in the current set of configuration is around 65%. And then you have 2% decrement on various efficiency contour. Right, once you move the marker, on these plots here, you can read out the marker. You can read out the numbers using this marker readout at the bottom. So there's one marker for power delivered, another marker for PAE. So that's this much section. Now, for a quick estimate or quick information, if you are looking at the load condition where you are getting the maximum power and perhaps the maximum gain, you can look at this window. So this gives you Z load. So that's the load impedance your device would like to see in order to give you 41.5 dBm power in the output. And at that point, the gain of the device is around 12.5 dB. That's the input impedance for the device. And so once you have this information, there is really no necessity to go and perform source pull, because this is what you try to do in source pull to find out the right input impedance of the device to obtain, kind of good amount of gain. And at that load condition, the efficiency which you're obtaining is around 57%, which is pretty good, right? So hopefully this is clear. Similarly, like in certain other power amplifier design considerations, you might wanting to design for the maximum efficiency. So these are the conditions where you can obtain maximum efficiency. And you can see if you go behind efficiency, you will have lesser power as compared to the condition where you had. But at the same time, you will have a better efficiency. So again, like we saw in the low noise amplifier video, there is always a compromise between noise figure and S11 and so on. Similarly, in power amplifiers, you make your own choices. You have to have a good compromise between efficiency, output power, and then later, once we start the power amplifier design videos, you will see even the S22, IMD, ACPR, all these things have to be compromised on. And you need to find one unifying point where we can get best of all worlds to do a proper PA design. Now this section here is pretty similar to what I showed you earlier. So these are the circular region where we have swept, and these are the grid points where we have actually simulated our harmonic balance or performed the load pull. And these are the gain contours. So once you start moving the marker here, you can see this readout will get updated according to where you are. And you can observe in the entire region, what is the gain, what's the load, what's the output power, and the efficiency. So hopefully, let me zoom out again. Hopefully you have this half part very, very clear on this data display. Now let's turn our attention to the right hand side of this plot. So what's this plot? Well, basically, if you look at the maximum power condition, let's say you found the maximum power is available in this region. If I set a complex conjugate, and this plot is going to give me the zoomed in view of the region around where I want to operate. So the Smith chart, it can be, it's a normalized plot, and you can unnormalize it to any impedance. So I'm going to unnormalize it to this impedance so that I have a zoomed in view of this region. Now in this particular case, it's kind of still okay, but in some LDMOS or certain GAN devices, you might be operating very close to the periphery of a Smith chart, and that doesn't make your job much simpler. But by bringing that operating impedance to the center of a Smith chart, now suddenly you can have a more comfortable view of looking at your data. On the right hand side, the data which is available in a polar kind of plot like a Smith chart, we expose this information on a rectangular X and Y. Now here you can see very clearly the contours, and if you are looking at a good compromising point where you can get a good efficiency, like in this case I'm getting efficiency of 58%, and if I place my marker on the contour which is actually cutting this efficiency contour, you can see you are obtaining 40.2 dBm. So if your design goal is to obtain more than 40 dBm power and efficiency more than 55%, this impedance point, or 28.2 plus J12, is the ideal load condition point. So rectangular plots are easier to understand, and that's what they give you. Now, lastly, the bottom right part here is again, plotting this circular data of gain contours in the region and in the Smith chart, which we use for simulation, to be plotted on a rectangular XY. As simple as that. Now remember we talked about equations to plot power and efficiency contours. So these are the control variables. You can select what kind of power step you would like to use to see contour, how many power contour lines you want to see, PAE contours as well as the gain contours. So using these variables, you can adjust the detail which is available in these plots. For example, if I only want to see 5 power line contours, and basically you will only see the 5 lines there. Now this information, you look at the another tab here. So there are a bunch of equations which are doing this post processing automatically for you. So as a designer, you don't need to write these equations. But once you start with basic harmonic balance, it's nothing but using the similar functions behind the scene like I showed you in harmonic balance, and it is doing all kind of data post processing. Now, as a designer, you really don't need to be concerned with these equations, but if you have watched my earlier videos on multidimensional data processing, and if you want to really understand some of these equations, if you proceed one by one, you will be able to figure out, because this is nothing but kind of a multi dimensional array mathematics working behind the scene to give you the data which you are seeing on this data display plot. Finally, on the third page of this data display, this is a simpler data available. If you don't want to see a bunch of data at the same time, here you can get the key snapshot. So here, when you move the marker on the power delivery versus PAE plot, so on the y-axis, you have a power delivered. On x-axis, you have the PAE. So depending upon where you want to be here, you can see the things moving in Smith chart, and also this data will get updated. The readouts will get updated. So again, this is another way of looking at the information what you're looking for. All right, so this was fundamental of load pull. There are plenty of advanced things in the load pull design guide. You could do, swept available source power, look at EVM contours versus source power, plot contours as XDB compression, and so on. So we will cover this and lot more advanced topic of load pull simulation in the next video, which you will have, shortly. But till then, just make sure you are comfortable with running the basic load pull. Because once you're comfortable looking at this basic load pull, rest all the other load pulls are basically going to build upon this basic capability and do either the source power sweep or the bias voltage sweep or the frequency sweep in case you are doing a broadband kind of amplifier design. Then your impedances on which the power is available at the output versus frequency is also going to vary. So all those multi-dimensional things we would be very comfortable building upon. But the first thing first, you need to be comfortable with this load pull, and then in the next video we are going to talk about some of the more advanced capabilities what ADS can offer you in terms of load pull analysis for your successful power amplifier or any other nonlinear circuit design where you may be wanting to use load pull. All right, so that's all for this video. I try to cover all the points and hopefully it gives you the required amount of clarity which you are looking for while understanding load pull and trying to design power amplifiers in ADS. Thanks a lot for watching this tutorial. And again, don't forget to give it a thumbs up and subscribe to my channel if you haven't already done so. Wish you all the best in your design process.